So any questions about the exam? No? Scenario 1? It's interesting. Normally there's at least one
I have
question.
a question. It's not about the exam. So are we just going to not finish the minimum spanning trees slide set?
Correct.
Cool.
Basically, my shit, we only have a week left sort of instinct has kicked in, and honestly, I really don't think that this will be an algorithms course unless we at least talk about shortest path algorithms. So, so I'm going to jump into those because basically, once you know Prim and Kruskal, you've got the minimum spanning tree pretty well. So, question.
What's the format?
The exam will be a multiple choice exam. You will fill it out on a Scantron optical scan sheet. The questions are not as calculation heavy, and if you have a good intuitive understanding of the algorithms, you'll probably get most of the questions right. Question.
How many multiple choice are
Between 50 and 60. Next question. Yes.
So from the previous lecture, all we need to do is maybe review the first 20 slides of each talk, and that's all we need to know for the final.
Yeah, we'll only go as far as Prim's algorithm. This stuff isn't going to be on the final, so everybody leaves.
I'm sorry, I couldn't hear. You said this is not on the final?
Correct. I am not going to test you on shortest path algorithms on the final. However, shortest path algorithms are still very, very, very useful, so I highly recommend paying attention. You can tell how useful shortest path algorithms are because on Friday there were people asking questions in class indicating that they were confusing minimum spanning trees with shortest path algorithms. So, if that makes sense, shortest path is really important. Yes?
Do you need a cheat sheet like the midterm?
One sheet, double-sided cheat sheet. Yeah, just like the midterm. In my opinion, the exam is a bit of a softball, but you know.
That's what you said about the midterm.
Yeah. I've learned this semester that, like, I don't know what you guys would do if I threw you a hardball. Please, what I consider to be a hardball anyway. And really, it's the pitcher who decides what the pitch is. But you know. Anyway, enough of baseball metaphors. Any other questions? I think the time that's allotted for the exam will be more than generous. Frankly, I don't think 80 questions would be, you know, out of place, but, you know, I only have so much time to write questions right now. So, so shortest path algorithms then. Just to, are we recording?
Yeah.
Awesome. Just to, you know, recap the decision that's been made about the course content going forward. I've decided to cut off our discussion of minimum spanning trees at Prim's algorithm. We're going to get into shortest path algorithms because they're extremely useful. They're also extremely not extremely complicated. They're decently complicated. So, you know, they're just generally very useful. So, so we're going to apply shortest path algorithms to directed edge-weighted graphs. So if you'll remember if you sort of recall the general theme of the graph algorithms we've been studying so far, we started with undirected, then we did directed, then we did undirected edge-weighted, and now we're doing directed edge-weighted. So, you know, just not to dwell on these too awful long. But if you have a edge-weighted digraph, and you have 2 points in that digraph, an interesting question is, what is the shortest distance between 2 points? In this case, it's not a straight line. Question? Oh, yes, yeah, I'll post this to have it. So the shortest path problem, in general, given an edge-weighted digraph, find the shortest path from some node S to some node T. Generally, S is called the source, T is called the sink. A generalization of the shortest path problem, rather than find the distance between a point and another point, find the distance between a point and all other vertices in the diagram. It turns out that this is at the time and space complexity for solving the general shortest path problem is the same as solving it for one vertex. Anybody have any idea why that might be the case? That we need to solve the general case in order to find the specific case of the shortest path to one node in the graph. Yes?
Because anyway, we need to go through all the nodes and all the edges.
Mm-hmm. So, yes, essentially. So, in order to find the shortest path between one point and another point, you will have to travel through a number of points to get there, right? Any point in the graph may be in the shortest path to any particular point, right? Therefore, the shortest path to the intermediate points in the graph may form part of the solution to the shortest path to the point you're looking for. Therefore, in order to find the shortest path to a particular point, we must find the shortest path to all points in the graph. Make sense? Sort of? Maybe a little bit? Let me see if this is... Yeah. I wonder what's going to be on the exam! Don't worry, the entire exam is not composed of me quizzing you about shell-sort H-gaps. Only half the exam is me quizzing you about shell-sort H-gaps. I'm obviously being sarcastic. I'm not going to quiz you to that degree on shell-sort H-gaps. Although, you know, I'm not ruling out the possibility of quizzing you on shell-sort H-gaps. I've probably said enough. I've said the word H-gap enough. Anyway, good. So, I'm going to just sort of quickly jump through our representations. Our API, of course, has directed edges rather than undirected edges with weights. We have, this is a class for the directed edge itself, so we've got the source, we've got the sink, we've got the weight along that edge. The edge-weighted digraph is composed, of course, of a collection of directed weighted edges. We have an adjacency function in the same way that we've had adjacency functions before. It just tells you all of the vertexes which are adjacent to the vertex that you are considering. And remember, of course, that in digraph land, if you have a graph looking like this, this point is adjacent to this one, but this one is not because the arrow is in the wrong direction, right? It's just where you go to next. That's what adjacency means in a digraph. So, edge-weighted adjacency list representation, of course. The big difference, of course, between this representation and the one that we had previously is it's actually the same difference as the difference between an undirected adjacency graph, or adjacency matrix, and a directed adjacency matrix. We no longer have the doubles, right? So, going back to our graph that this is based on, 0, 2 is an edge, 0, 2, but you'll notice 2, 0 is not, right? Make sense? So far, so good? So, there are several important properties and assumptions that we make for directed edge-weighted graphs. Number one, paths are directed, obviously. A shortest path must respect the direction of edges, obviously. Weights are not necessarily distances. The edge weights might represent time or cost, or they could just represent distance. It's entirely up to the graph. Not all vertices need to be reachable. If some vertex is not reachable with respect to the source vertex, then we simply say there is no shortest path to that vertex. We, in programming code, we call that either a null or an infinity value, one of the two, and we call it a day. Shortest paths are not necessarily unique. There may be multiple paths of lowest weight from one vertex to another. In the case where there is ambiguity of this nature, we are content with simply finding one of them, all right? And it doesn't matter which one. So whichever shortest path is magically and conveniently given to us first by whatever algorithm we're about to study, that's good enough for today. Make sense? So far, so good? Good. So, given an edge-weighted digraph and a designated vertex S, a shortest paths tree, which is quite the mouthful, I'm probably just going to call it a shortest path tree. A shortest path tree for a source S is a subgraph containing S and all the vertices reachable from S that form a directed tree rooted at S such that every path through the tree is a shortest path in the digraph, which is quite the description. A shortest path tree solution exists, which we'll talk about. So, this is in contrast to a minimum spanning tree. In a minimum spanning tree, we are interested in calculating the spanning tree with the lowest overall weight, right? Here, we are interested in calculating a tree where the path to each node is as small as possible, and it's not quite the same thing, right? So, it's going to be difficult to come up with a good example on the fly. So that's a minimum spanning. Oh, no, it isn't. You know what? Never mind. We'll just keep going. That's the type of example one needs to have worked out beforehand. So, anyway. So, we can represent the shortest path tree with two vertex index arrays. Number one, distance to, is a length of shortest path from S to V, where V is the particular vertex that we are dealing with. So any vertex in the graph can be V. In the figures, this weight is associated to the vertex V. Edge 2 is the last edge on the shortest path from S to V. So, we are concerned with two things. Number one, maintaining what the actual distance to the node is. And two, how did we get here from the most recent node we visited? Turns out that this is actually sufficient. The goal of the algorithms is to compute the smallest, or the shortest path tree. That is, to compute the edge to and distance to arrays. Once we have computed these arrays, then we have, all we need to do is look up the particular node that we are trying to find the shortest path to, and boom, we have our answer. So, to compute the shortest path tree, two techniques are helpful. Number one, edge relaxation, and number two, vertex relaxation. So, in general, the technique that we're about to employ, sort of from a very broad perspective, we set ourselves up with a spanning tree, right? So a tree that touches all of the vertexes in the graph, and of course must, we have the, by necessity it also is touching the source vertex. And we perform a series of refinements of this spanning tree in order to eventually calculate the shortest path. Okay? So, edge relaxation. Distance to V is the length of the shortest path known from S to V. So we've already made a slight modification. So instead of having all of these guys be blank and then calculating them out as we calculate the tree, we've now introduced an idea that these guys might be inaccurate and need refinement. So we are no longer assuming everything in the distance to array is correct. All right? We're assuming that it might need correction. So, that correction is known as edge relaxation. So, distance to V is the length of the shortest path known from S to V. Distance to W is the length of the shortest known path from S to W. So, we have distances to two vertexes in the graph. Edge to W is the last edge on the shortest known path from S to W. If E, some other edge in the graph, goes from V to W and gives a shorter path to W through V, then we update both distance to W and edge to W, in which case VW is called the eligible edge. Otherwise, it is called an ineligible edge. So that's some mighty pretty words from a set of slides. So here, this is the idea. Let me just get the half-decent chalk. Boom. So let's imagine we have a graph. This will be S, this will be V, this will be W. This is a very simple example meant only to illustrate this particular property we're talking about. So let's say we've got 2, 2, and 3, and then 4 and 7. So, what's our, so let's assume we haven't calculated this edge here. We'll call this edge E, all right? What's the shortest path to V before we've considered E? What's the length of the shortest path? Four, thank you. So edge 2 and distance 2 for V and W. And, we'll just be concerned about those. So, distance 2 is 4. I guess I will have to label the nodes, won't I? So, what's the value of edge 2 for V? It's an edge, right? You have to specify 2 vertices. What are those 2 vertices? 1, 2. Good. So let's, assuming that E hasn't existed so far in our calculations, the distance to W will be 11, and our final edge to W will be 3, 4. Now, via edge relaxation, it's, relatively straightforward, actually, as if you break it down in terms of its basic operations. So we want to calculate the distance that, the new distance to W, right, from V, including this new edge E, right? So, you take V and you add the edge of the weight of the new edge, right? That'll make it 7. We then perform a Boolean test. Since 7 is less than the existing distance to W, we know that this is actually a shorter path to W than to go through 3. Right? Despite the fact that more edges are involved, we're not interested in the number of edges involved, we are only interested in the weight of the edges involved. Right? So despite being a technically longer path on the diagram, it's still a shorter path in mathematics. Making sense? Good? So, because 7 is less than 11, we overwrite 11 with 7, and we overwrite the last edge pointing to W with the new one, 2, 4. Make sense? Question?
Why would we not consider a G from the scanner?
You remember how in Prim's algorithm we sort of start at one point and then fan outwards? That's kind of what we're going to do again. So we're basically, we're going to be constructing the spanning tree as we're performing the relaxations. So that's why we'll have edges that, like when we'll be at a point in the algorithm and then we'll have several edges to consider, and then we'll just consider those edges, and then we'll move on, consider that point dealt with, and move on to the next point.
So we just haven't gotten to that yet, kind of?
Yeah, that'll come into it when we put everything together. Yeah. Question? No? Okay. Any other questions? Okay. So that's edge relaxation, right? Here's another example of that, but I kind of did one on the board, so who cares? So, additionally, vertex relaxation. All edges pointing from a given vertex are relaxed. An edge from a vertex whose distance to V entry is finite to a vertex whose distance to entry is infinite is eligible and will be added to the edge 2 array if relaxed. So, basically, vertex relaxation is a combination of things. This distance to entry is finite, distance to entry is infinite. Doesn't make sense yet because the slides are like putting things that are later in the algorithm earlier in this description for some reason. Basically, when we start up a shortest path algorithm, we have to initialize edge 2 and distance 2 with something. So what we initialize what we initialize distance to is infinity, because infinity is greater than everything. So if you have a distance to being infinity, that means that either the vertex hasn't been considered yet, or it's actually not accessible from the source node that you selected, and the algorithm might be finished. Make sense? Good. So, an edge from a vertex whose distance to entry is finite to a vertex whose distance to entry is infinite, that is to say, from a vertex that's currently in the spanning tree to one that we wish to be in the spanning tree, is eligible and will be added to edge 2 if relaxed. So we add this to edge, so basically, whenever we encounter a vertex that does not have a distance to already calculated for it, we just gobble it up. We assume that whatever vertex we're on, that's currently the shortest distance that we know about to that node. Now, it's not guaranteed to be the shortest distance to that node, right? There may be other nodes that get there faster, but it's kind of like the way that we trace through these graphs is going to feel a bit breadth first searchy, if that makes sense. So we're going to sort of fan out. We're not going to do a depth first search approach here. So longer paths that end up being shorter, which let me rephrase. Paths that include more vertexes but have a lower weight than paths with fewer vertexes will show up later in the algorithm, right? But in order to perform this comparison and to consider these edges, which we're going to add later, we need to sort of establish what the baseline shortest path is, which means that basically we're taking a greedy approach. Anything that doesn't have an edge to it, anything that doesn't already have an edge to it gets an edge upon first examination. Does that make sense? Good? So far? Anyway? Okay. So, we'll talk very briefly about the minimality conditions. This should be reasonably intuitive from the words shortest path, right? But, so let G be an edge-weighted digraph. Then distance 2 are the shortest path distances from S if and only if distance 2 of S is equal to 0. The distance of the source to itself is 0, obviously. For each vertex V, the distance to V is the length of some path from S to V. For each edge V to W, distance to W is less than distance to V plus E dot weight. So basically, if you take another way of saying this. Let's say we had a couple of vertices all pointing to W, right? This is the shortest path to W if and only if there is no path through any vertex of lower weight, right? So if we do the edge relaxation comparison on every other edge entering W, we will find none of these will modify the array. That this comparison between the distances will fail to on each of the additional edges which are considered. Then it's the shortest path to that one, right? Make sense? Should make sense. A little bit mathy, but there you go. So, we'll skip the proof. The previous proposition shows an equivalence between the global condition that the distances in distance 2 are shortest path distances and the local condition that we test to relax an edge. Hence, the optimality condition leads immediately to a generic algorithm that encompasses all of the shortest path algorithms that we consider. For now, we consider non-negative weights. So, our generic algorithm: initialize distance to S at 0 and distance to V at infinity for all other vertices. Repeat until optimality has been achieved. Relax any edge. So what's the immediate question? In what order? In what order do we relax edges? Right? So, there are three different approaches which you can take to deciding which edges to relax in what order to produce the shortest path. You have Dijkstra. It's not Dijkstra, it's Dijkstra. It's a Dutch name. Dijkstra's algorithm, only applicable if you have all of your edges with non-negative weights. You have topological sort shortest path algorithm, which must contain no directed cycles, and the Bellman-Ford algorithm, which must contain no negative cycles. So, topological sort, we can use this to produce a shortest path algorithm, but of course, remember that there is no topological sort if there are cycles, so that's the restriction here, right? We're going to talk about Dijkstra. So, Dijkstra's algorithm outline. We consider vertices in increasing order of distance from S. That is to say, the non-tree vertex with the lowest distance to value. Add the vertex closest to S to the shortest path tree and relax it. That is, relax all edges pointing from that it. That's some tasty grammar. So, essentially, very sort of hand-wavy description. We're, under Dijkstra's algorithm, we're not deciding which edges to examine. We're deciding which vertices to examine, right? Dijkstra's algorithm has this nice property that once a vertex has been fully examined, it does not need to be examined any further, right? And basically, we take a vertex, right? We take all of the edges going out from that vertex, and we see if those become the shortest paths for any of the nodes that this node is pointing to. So when we are examining a vertex under Dijkstra, we're not actually modifying the shortest path to that vertex. We're modifying to the shortest paths we're modifying the shortest paths to the nodes adjacent to the vertex that we are examining. All right? This will make more sense once we do an example. So the question then becomes, in what order do we examine the vertices? And the answer to that is we maintain a priority queue of the vertices by minimum edge weight. So whichever vertex is currently has not been processed and has the smallest edge, the smallest distance to so far, that's the next vertex you're going to examine. Make sense? Shall we do an example on the board? I'm going to use a marked array to determine whether or not we're done with it, right? Distance 2 and edge 2. All right. Note here, I've got a bidirectional edge with one weight going one way and another weight going the other way. Just, that's possible. Just want to throw it out. So, give me a node, any node.
0.
0. That's boring, but okay. So this will be our source. Distance to the source, 0. Edge, nothing. Everything else, currently, 1, 2, I could do the grid lines, aren't I? All right. So, we begin our examination with S. Right? So we have two vertices which are adjacent, 6 and 3. So starting with 6, ordinarily you'd have like the adjacency matrix and you'd be going in order of that, but who the hell cares? Six, distance 2 is 3. Edge is 0 to 6. Good. Other one, 3. Distance 2 is 2. And it's 0 to 3. Good. Oh, that's the wrong column. Jesus Christ. Can you tell it's a Monday morning? There we go. There we go. All right. Now, the next one we go with the minimum vertex that has not yet been checked off, which is 3. Very good. So, 3. How many? What do we got for adjacency? We've only got 4. So 4. Distance to 4.
9.
Yeah. Or no, sorry, 9. Yeah. That's distance from the source, right? Distance from the source. So 4 has distance 9. Size is, or the last edge leading to it is 3, 4.
Wrong.
Oh. 3, 4. All right, and that's 3 checked off. You know what it is? It's because it's a bigger box. But anyway, okay, so we've done this one, we've done this one. So what's our shortest path of unmarked things? 6, because it's 3, right. So what's adjacent? We've got 2 and 5. So let's do 2 first. Distance to 2. Right? 1 is the distance from 6 to 2. What's the distance from S to 2? That's right, it's 4. And we got there, but via 6. Now for 5. We've got, what's our distance?
6.
Yes. 6, and we got there from 6, ironically enough. And then that, any more, and no, okay, so check. There we go.
What about 3?
Where's 3? Oh, heck, yes. Pardon me. Okay, yeah, so we've also got 1 there. All right. So, examining 3. What's our distance to from 6?
4.
4. Is that greater than 2?
No.
No, so we do nothing. Check it off anyway, but good thing we examined it. Yes, thank you. Good, so 6 is now good. What is our minimum path, what's our minimum distance of the remaining nodes? This one. So we are now examining 2. 2 is here. We only have one adjacency vertex to consider, going back to 6, which, you know, let's go through it. So 6 is already checked off, so, well, yeah, you know what, it's marked, so we'll just not worry about it. But you know, if you did the math, you'd see obviously that, you know, going back here and then back again is longer than to just stay there. But yeah, so 2, fine, nothing, check. Shortest distance to 2 is 4. Good. Next, what's the next largest? 5, right? So 5 here. What do we got in terms of adjacency? We've got 2 and we've got 1. So 2, right? Is 6 plus 4 smaller than 4? No, so we do nothing. This one actually isn't in the thing yet. So we've got 6 plus 8 is 14. 14 goes right there. 5 gets checked off. I hope you'll indulge me for like 2 extra minutes while I finish this example off. The next shortest path, 14, right? 14, 2, obviously 6 plus 9 is not going to be less than 4, so that's fine. And then 1, we've got a 2 going back to 6. 6 is marked, so we don't care. Oh, I forgot to do the edge too, so that's 5 to 1. So there you go. Dijkstra's algorithm. You're welcome. Slash do exam review, maybe, I don't know, whatever. Usually I do a class of exam review, so.
Is Wednesday the last day of class, or is it Thursday?
Yeah, I think Thursday's the last day of classes, so Wednesday will be our last class.